Okay, so last class, you remember where I think we had discussed what are called equipotential surfaces. And then this is just a revision. I just wanted to go behind a little bit for the sake of continuity. Okay, so we said that equipotential surfaces, as the name suggests, the equi means equal, potential means that, you know, the potential as we have understood it in this course. So equipotential surfaces simply means the surfaces that are at an equal potential. And then we say that equipotential surfaces are always perpendicular to the electric field. So for instance, if you have, let's say you have the electric field in this manner, any line that is drawn like this, you can see that it is actually perpendicular to the electric field, so it makes up an equipotential surface. In a similar way, if you have the electric field radiating in all directions, as shown in this diagram here, then if you draw a spherical surface around this charge, then you see that at all points of the surface, the electric field is going to be perpendicular to that particular surface. So therefore, all the points on that sphere make up an equipotential surface. Just 1 minute, excuse me. Hello? 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 Hello, class?
We can get you, sir.
We can get you.
Okay. Okay, so this is basically what we discussed last time, and I left you with this homework. Did you guys try it out, this homework? You are still not ready? Okay, since you are still not ready, I'll skip it again, and then you let me know when you're ready. The other thing that we had discussed was we calculated the electric potential due to a point charge. So I think I'll not go through the steps, but then I just wanted to emphasize this equation is very, very important. Now, have you seen how we are progressing? We are, you see, you could see that at first we computed the Coulomb force. Remember, at first we computed the Coulomb force. We said that the Coulomb force between two charges was just K, and then Q1, Q2 over R squared. That was the Coulomb force between two charges, two-point charges, Q1 and Q2. And then when we came to the electric field, we said that the electric field was basically the force per unit charge, So when we discussed the electric field, we said that the electric field was actually given, the electric field due to a point charge. The electric field due to a point charge was just given by K, and then that point charge over R squared. Remember this this formula, I'm sure. So you know, if you know the Coulomb force, just by dividing by the test charge, then you could find the electric field. Okay, so the equation for the formula for the electric field due to a point charge is just given by that. Now, have you seen the symmetry in this? Here there is just one Q. Here there are two Q's in the numerator. Okay, now look at the formula for the electric potential for a point charge. Remember, this could just be written as V is just equal to K, and then times Q over R. Now look at this. This R is now no longer squared, it's just linear. So you can. So there are 2 points that I want to make there. The thing is that you can see it's easy to remember these equations because they have got a certain nice symmetry. The next thing that you could note is that these things are cumulative. For instance, if you don't know how to calculate the electric field, then you cannot calculate the electric potential, because you remember the electric potential, we just said that is just equal to minus, and then this. You remember this formula that, so it means that if you don't know the electric field, this guy here, then you cannot find the electric potential. And if you also don't know the electric force, which is the Coulomb force, you cannot sometimes find the electric field. Okay, so now today we are starting our class on how to now apply superposition principle. If you have a number of charges, how to apply superposition principle in order to find the total electric potential due to two or more charges. Yes, Mr. Mchimba, I can see your hand.
Yes, sir. The first thing I just wanted to find out, I didn't understand the point where I think you stated the last time we met that the electric fields always moves to the decreasing electric potential.
Yes, please.
Yes, I did not understand clearly on that point.
Okay, now, Mr. Mchimba, I think I had asked to say any problem arising from the previous class. That was a very nice opportunity to pose that question, because now the class is already on. For me to go back, then I'll have to. What are you saying? I think all the time when I ask that question to say that any problems arising from the previous class, then that is the opportunity to bring up those issues. Now the class is in motion, this one already, but I'll try to see if at the end of the day I can find some time to address that.
All right, sir.
Okay.
Then also the slides, sir, you should put them on Moodle.
The slides? Okay, but yes, you didn't see the slides. I think that I had posted them in the group. I was reluctant to put them on Moodle because I know everyone is on this group. So did you access the ones that I had posted on the group?
No.
Huh? Yeah.
No, sir.
Okay. What about the others? Did you see the slides that were posted on our Telegram group?
Yes, sir.
Okay, so Mr. Mchimba, then just check on Telegram. I think the slides are definitely there. And I'll make an effort to also post them on Moodle, because Moodle is our formal platform, but I just took it for granted because I knew that I had already given you.
All right, sir. Thank you, sir.
Okay. All right. So now what we're trying to say is that what if you have if you have more than one charge in a certain area, then how can you find the electric potential due to those charges? So basically what we are saying is that, let us say that you have the charges that look like this. Okay. And let us say that you have the charges that okay, so I have the charges, this one, I say it is my first charge. I have this as my second charge. I have this as my third charge. So let me say this is my Q1. I have this as my Q2. I have this as my Q3. And then I have a certain point of interest. Let me call this point as P. I have a point P. That is not a charge, it's just a point. So I want to find what is the electric potential at the point P due to charge 1, charge 2, and charge 3. Okay? So the equation, the principle of superposition will still hold. You see, because I know the distance from there to there, I can actually call it my R1, I know the distance from there to there. I can call it my R2. I know the distance from there up to there. I can call it my R3. So what does it mean? It means that according to the superposition principle, I can find the electric field. The total electric field at this point P is the sum, a vector sum of the electric field due to Q1, Q2, and Q3. So basically, what we do is that we know that the electric potential is actually given by minus the dot product of the electric field and this path integral and this path element. Okay, so now you see from the superposition principle, it means that these you have to add all these electric fields due to 1, 2. So whenever you see a summation, it means that you are just basically adding the electric field. Okay, so what does it mean? It means that what it means is that the total electric potential is just a scalar. It's just an algebraic sum of the potentials due to each of the particles. Okay, so what does it mean? It means that if I find the V1, you know, V1 can actually be written as, it can be written as K and then Q1 over R. Remember from our equation for potential, this is nothing but K. So Q over R. So in this case, I can say this is V1 and then V2 can be written as K times the Q2 over, by the way, I must write R1 here. And then I write R2. I can also write an equation for V3. And then it means that the total potential at that particular point, it will just be a sum of V1 plus V2 plus V3. So basically, this is what is called the principle of superposition as applied to the electric potential. One thing that I want to emphasize here is that, you see, when you are talking about the electric field, when you apply superposition principle, the total electric field due to a distribution of charges is a vector sum. Underline the word vector when you apply it to the electric field. But then when you come to the electric potential, by the way, the electric potential is a scalar quantity. So since the electric potential is a scalar quantity, it means that when you apply superposition principle, you are actually just adding these the electric potentials due to each of the following, due to each of the charges. You are just adding them arithmetically, not vectorially. Okay, any questions? Maybe let me pause. Any questions or contributions or anything?
Hello, sir.
Yes, please.
But you also need, for example, maybe to consider maybe the negative and positive.
Exactly. That's a very, very important. That's a very, very important point that you have brought. So when we say it is, I said that the
Hello, sir. I think we can get you.
We can't get you, sir.
Okay, can you get me?
Yes, sir.
Okay, so I was just trying to respond to that question. I don't know, was it from Mr. Mchimba? Okay, about the,
yes.
You know, when we talk about this, I had talked about said that the electric potential is basically an arithmetic sum. So what does the word arithmetic sum mean? It means that if the charge, say one of the charges is the negative, it means that the potential that is going to contribute at this point P will be a negative. So what I was trying to say is that it's a sum, so when you say plus a minus value, when you have a plus, when you're adding a minus value, you know from your grade 8 work that the plus and the minus, it gives you a minus. Okay, so it means that the minus sign will override. So when you're adding, of course you're adding, but then it will be an arithmetic sum where the minus will override in case you have a minus. Is that clear? Is that clear?
Yes, sir.
Okay, so I think this is making me feel quite very, very lazy, just in case you didn't know. And it's really quite demotivating when you're talking to people and then it's like they're sleeping. I really like the feedback because, you know, from time to time the network may go and I may remain talking to myself. How do I know if I'm not getting the feedback from you people? Okay. Anyway, let us proceed. I have a question here. Which of the following figures have potential 0? I think this is quite a very, very good question. So which of the following figures has this V is equal to 0 and E is equal to 0 at the red point? At the red point. So is it A, is it B, is it C, D, or E? Do you want us to do it together? You advise me if you can do it on your own so that we proceed. Can we do this?
We can do it together.
Okay, so now I'll give you a minute. I think let me give you 30 seconds to think about it, and then you give me your submission. Okay, so what do you think? Anyone?
C, sir.
Huh? So the answer
C.
is C, yeah? Okay, the answer is C. Is that the feeling for everyone? Does that represent the opinion for everyone?
D.
So some people think that it is D. So we have another school of thought that thinks that the answer is D. Okay, so the one for C, why do you think the answer is C? Why do you think the answer is C?
D, sir, not E.
Oh, someone said D. Okay, all right. So who wants to start first? The one for D? Can you tell us why you think the answer should be D? As they are thinking, can I come to the one for C? The one who had mentioned the C. What is your argument? What is your reasoning? Okay, as they are thinking, anyone else? Anyone else? Okay, so I'll give it as an assignment, as an exercise. You go and think about it. And then when you have thought about it, we can come back and talk and discuss. You will let me know. Okay, so now what we have discussed so far is the point, the discrete charge distribution. We say that the electric potential V due to a point charge. Oh, okay, Mr. Katito, you have something to say.
Oh, I just wanted to say the reason why C was the answer.
Oh, you want us to go back? Okay, yeah.
Yes, but sir, I only have the solution for why the electric field is equal to 0.
Oh, sure. Please go ahead and tell us.
Yes, so what I'm thinking is maybe since for all these charges they are producing electric fields, so these electric fields in between here they'll be canceling. So that's the reason why the electric field
Canceling
here
out.
is
Like that. So for this C, for option C, so we are saying that the E cancels out. I like that. So the E cancels out, and then just to help you, it's because of the symmetry. So you can see that there is a certain symmetry in the problem. There's a certain symmetry. There's a certain symmetry in the problem. So what we mean by that is, you see this guy, this charge here, it will be producing an electric field in this way, in that direction, since it is a positive charge. So, but then there is also this charge at the corner here, it will be producing the electric field at this. Now you see, since these charges are equal, and these distances are the same, because you can see that this is a square, so these distances are the same. So it means that these two electric fields are going to cancel out. Okay, so that is coming from the symmetry. In a similar way, the electric field due to this one and this one also cancels out. That's a good one, Mr. Katito. So it cancels out. So you find that the electric field is equal to 0. So here we have this one for part E. Now, what about anyone who wants to say about the V, the potential? I think we are all agreed that the electric field will be equal to 0. But then is the electric potential also equal to 0? Yes, Mr. Sinyenza. Mr. Sinyenza, your hand is up.
Yes, sir.
Yes.
I feel the answer is going to be D.
The answer is no. The answer is going to be
E.
The answer is going to be E. So you have gone for this one.
D.
Or you are saying that the answer is going to be D. Okay.
D, yes.
Why D?
Because according to the expression.
Now, before you go to D, Mr. Katito, can you say something about the electric? Can you say something about the electric potential for part C? Because we are trying to work on part C and see why it is the answer or why it is not the answer. So we have seen that the first condition here for the electric field has been satisfied. Can you say something about the electric potential at the red point?
So the electric potential for part C, I think it will be adding up. Because the charges are positive.
Okay, very good. So
charges.
very good. So for part C, you see what we had said was that the total V, it will just be equal to V1 plus V2 plus V3 plus V4. And now it will depend on the sign of the charge. If the sign is positive, then it will be the V will have a positive sign. If the charge is negative, then the V will have a negative sign. Now you can see from here that all these are positive charges. So in short, and they are equal. So you can just say that this is just same as 4 times V1 if you want, 4 times V1. And then what is V1? You can say 4 times Q1 over 4 times K Q1 over R. So you can see this is not equal to 0 because everything here there's nothing that is equal to 0. So this cannot be equal to 0. So it simply means that this one, it cannot be the answer, this C. Thank you very much for that. And then I think Mr. Katito has even given us a hint. Thank you very much. So if you look at part D properly, the electric field will be canceling out because of symmetry, as we had already discussed. You see that here, the electric field, due to this guy, the electric field, it will be in which direction? It will be Remember that for a negative charge, the negative charge acts as a sink. Okay, remember that there, the negative charge acts as a sink for the electric field lines. So here the electric field lines will be in this direction. Another one will be in this direction. So you can see that they are equal magnitude but opposite direction, so they will cancel out. But then for this one, the electric field lines will be in this direction. I hope we are all together. So this can cancel out. So we know that the electric field will be equal to 0. Now, the electric potential, you can see, let us talk about the electric potential, maybe even before we conclude that this is the answer. Maybe that could not be the case. Let us come to the electric potential. What is the electric potential? You know, one thing that you must know is that the electric potential is just equal to V1 plus V2 plus V3 plus V4. In this case, all of them, everything, V1, V2, V3, and V4 have the same magnitude, but then the only thing that can change is the sign. Okay, so so it means that what we have here is, allow me to just write it. Okay, maybe I can still squeeze it there. So I can say that the total potential is the potential due to this one. Let me start with this one. This one I can say that it is K times Q1 and then R, because the R is the same. The distance from here to here is the same. So is it, let me just remove the one. So this, is it negative or positive? The potential due to this guy, is it positive or negative? It's negative, so I'm going to put a negative here. So I put a negative. And then what about this one? This one is also negative, so I have K and then Q over R. This one is positive, so I have plus K and then Q over R. And then that one is also, this one is also positive, so I have plus K plus K Q over R. So what you can see here is that this is supposed to be a negative. So this cancels with that, this cancels with that. So the potential just becomes 0. So for here, both the electric field and the electric potential are 0. If you do this analysis for all these other diagrams, you are going to find that the electric, either the electric field is equal to 0, but the potential is not equal to 0, or vice versa. Okay, I can see two hands here. Is it, Mr. Sinyenza, your hand is up? Okay, it isn't, eh? It was just there. Okay, so now I think, unless there are any, yes, please.
I have a question.
Hello?
Can B also be answered according to explanation in?
Okay, so let us look at B. You've done well to ask, so that because very soon the time will even be up. So we, as we are waiting for the time to be over, we can be answering the question. Okay, so now let us, we are talking about the possibility of B being the answer, right?
No.
Are you suggesting that B could also be the answer, madam? B, this one, eh? So now let us try to look at B. What is the electric field? No, the electric field, you know, for the positive charge, the electric field line will be in that direction. Agreed? Agreed, madam? The electric field line will be in this direction. Okay, that is for them. What about for the negative? The negative, the electric field will be in this direction. Because, you know, the negative is a sink for the electric field lines. So the electric field lines are going to be in that. Now you can see that here, we are just it means that these are not canceling out. So the electric field will not be equal to 0 for part B. The electric field will not be equal to 0. Since they are adding up, they are not canceling out. So already we can see it's already disqualified because the electric field is equal to 0. But the electric potential, so here, the electric field is equal to, the electric field is not equal to 0, but the potential is equal to 0. So this one is satisfied, but the other one is not satisfied. Okay, so let us go for the break. Then when we come back, we have this this question that has to do with discrete charge distribution. Just a little bit behind. So what we had said was that if you have a continuous charge distribution, the best, you assume that this continuous charge distribution is made up of an infinite number of small elements. Okay, each of those elements could be considered to be a point charge with a charge of dq. So with a charge of dq. So it means that if you want to find the electric field, the electric potential at a certain point P, due to this entire charge distribution, first of all, you find the electric potential due to a very small, infinitesimal element that is called dq. All right, so you know that according to what we have learned so far, that will just be given by 1/4 pi epsilon naught dq over r. Okay, so what I was trying to say is that this dq here, it has a contribution. Its contribution to the electric potential at this particular point can be written as dV. Remember, V here is not the volume. V here is the electric potential. So the contribution of this small element to the electric potential at this particular point, we are calling it dV, and the dV can be expressed as 1/4 pi epsilon naught, then dq over r. Okay, so in order for us to find now the electric potential to the entire distribution, it simply means that we have to integrate this equation for all values of r. See, I was saying that this r is a variable because depending on where you place this element could be anywhere over this surface. So depending on where you place this, then the r from here to here could change, from here to here it could change. So this guy here is a variable, as well as the dq is also a variable. So when you integrate the right-hand side, you know 1/4 pi epsilon naught is a constant, so you can factor it out of the integral. Then what you just remain is with what you remain with is that. Okay. Now this dq here, depending on the configuration, the charge configuration, whether it is a linear charge distribution, surface charge distribution, or volume charge distribution, you can use any of these equations to express this charge that is here, the element of charge in terms of an appropriate charge density. Okay, so we're trying to look at an example where we have a rod of length L, and then we are told that it is lying along the x-axis, and it has a uniform charge distribution of lambda. So the question was saying that find the electric potential at a point P located on the y-axis at a distance d from the origin. So what we had done was that we just wanted to depict the situation. You draw a diagram. So this is your y-axis, and then this is your x-axis. Okay, so we said that this, according to the question, the way the question is, we have the rod. It starts from here. That is the origin, and then it has got a length of L. So the way we have drawn it, if it has a length of L, then this point here is basically the origin. So we say that it is x is equal to 0. And then this point here, just at the end of the rod, we can say it is the point x equals L, because that is the length of the rod. And then according to what the question is saying, we are saying that we want to find the electric potential at a distance which is along the positive y-axis, then the distance d. So from here, we are saying that we have d. Okay, so just by so doing, we have depicted the problem. So this is our point P, where we want to find the electric potential. We want to find the electric potential due to this line, which is charged. Okay, so what is the first thing to do? The first thing to do is to imagine that this charge distribution is made up of very, very, very small infinitesimal elements. So we took an element just here. We say that the length of this element, since it is along the x-axis, we could say that this element is dx, has got a length of dx, and then it contains a charge dq. Okay, so you find what is the electric potential? This one could just be considered as a point charge. So what is the electric potential? The contribution of this electric potential at that particular point P. So we say that could be written as dV is just equal to K, and then dQ over R. Say R is the distance from that charge up to that particular point of interest. Okay, where, of course, we know that K is nothing but 1 over 4 pi epsilon naught. Okay, so the next thing to do is this dq, we can say, but this dq can be written in terms of an appropriate charge density. In this case, since this is a line, then it is a linear charge density. So we say that this is the lambda times the x. That is the dq. It could be written like that. Now, you see, this R, as we had seen earlier, this R is also a variable. It could change depending on where you have taken this line, this charge, this element here. If you have taken it here, then the R will be smaller. If you take it here, then the R will be bigger. So R is a variable. So we also need to write it in terms of the other variable, which is x. Okay, so if you use Pythagoras theorem, you know that if the distance from here to here is x, the distance from here to here is d, then from Pythagoras theorem, this R is just basically x squared plus d squared, and then a half. It's the square root of x squared plus d squared. So if you substitute these two equations in the first equation, then you have dv is basically equal to k, and then lambda dx, and then over this x squared plus d squared, and then you take the square root. Okay, so if you inspect this equation very well, you realize this is a constant, this is a constant, and then the d is also a constant. So the only thing that is not constant is the x. So you can actually integrate. So if you integrate, then on the left-hand side, it will just be equal to v. On the right-hand side, I know k is a constant, so I'll factor it out. Lambda is a constant, so I'll factor it out. And then there's nothing else that I can factor out, so I just have to integrate this. This now dx over x squared plus d squared to the power half. So I'm integrating that. And then what are the limits of this integration? What is the smallest value that your x can have if you look at the diagram? What is the smallest value that the x can have?
0.
0. Smallest value is 0. What is the biggest value that x can have?
L.
L. Okay, so get like that. So you are now in the business. The only thing that is remaining is for you now to use your knowledge in mathematics. Use the knowledge in mathematics to evaluate this. So which method of integration are you thinking of? Which method?
Substitution.
Huh?
Chain rule.
We can use chain rule. Do we have an integration method that is called chain rule?
No.
Chain
I'm
rule
thinking of use
or
substitution.
differentiation. What method can we use? We can try U substitution.
Yeah, yes, sir.
Huh?
Yes,
I think so.
The U substitution. Are you sure it will be able to?
Yes. Let's try.
The U substitution could only work. The U substitution could only work if we had an x in the denominator, in the numerator here, because you know you are actually. So the U substitution, I do not think that it will work.
No, it can, sir.
Okay, let us try it. Let us try it.
It can, sir.
So we are saying that I don't write yet, but we're just trying it. So you are saying that we say let U equal to what? X squared plus D squared. Is that what you are saying?
Yes,
Is that
sir.
what you're saying?
Yes.
So it means that it implies that your du over dx will be equal to what?
2x.
To x, which implies that your du over 2 will just be equal to x dx. Am I right? Now, if you look at this x dx, you in the numerator, that's why I say that this could only work if you had x in the numerator, because in the numerator, what you only have is what? What you only have is x. What you don't have what you only have is the x. You don't have this x. Are you seeing what I'm saying?
Yeah, yeah. It's true.
So here we cannot use this. Okay, here what we are just going to use is the first principle. If you are integrating 1 over x, what is the integral of that?
Natural log of x.
It's the natural logarithm. Why is it that only one person is responding? Okay, so I think we are just going to use that kind of integration there. If you are integrating 1 over x, then the integral will be a logarithm. So in short, this we can also use logarithmic integration there, but the only difference is that we are going to add a constant in terms of x. Constant in terms of x. So I'll ask you to prove that, to verify that with your mathematics, but then if you integrate, this will become k times lambda, and then times the logarithm, of okay, can we think of another method to use to integrate this? Okay, so what have we done there? What we are saying is that we are just trying to use logarithmic integration, because we know that this, if you look at it carefully, it is just the same as 1 over the integrand. You are just integrating 1 over x. So the x in this case is x squared plus d squared. So I have the logarithm of this, but then because I have not taken into account the constant of integration, then I must introduce this term that is linear. Just try to convince yourself that this is the integral. If you are not convinced, try to go and think about it in your spare time, and then we can come and have a chat in the next class if you think that it's not coming out the way you want it to come out. Okay? Okay, so the limits here, as we have said, are 0 to L. So the next thing is to put in the limits. So we have k times lambda, and then the logarithm of, if I put now L, then I have L here plus L squared plus D squared to the power half. Okay? And then I'll say minus. If I now substitute the lower limit, you see this will be 0. This will also be 0. So in this, I'll just have d squared to the power of half, which will just give me d. Just look at it carefully. When I substitute this 0 here, 0 here, so I just remain with d squared. Then I take the square root, which just gives me the d. Okay, and just here I have so this k, you know that it is 1 over 4 pi epsilon naught. And then what is the lambda? Lambda, remember it's the charge, it's the linear charge density. It's basically the charge, the total charge per unit length. So it means that this can actually be written as the last step as Q over 4 pi epsilon naught L, and then times. By the way, I can even simplify this. I can simplify. How can I simplify this? Okay.
By distributing.
Yeah?
By distributing the half.
By distributing the half. This half, can I distribute it here?
Yes.
No? I can distribute the half here. So this one can be L, this one can be.
No, it's not possible, sir. It's not possible because there is a plus in between.
Yeah.
It's not possible.
Oh, that's not possible.
That will mean now we'll go to binomial.
Yes. So I think I can leave it here. L squared plus b squared, and then to the power half, and then minus d. So just by this, I know that I can now evaluate this. Because if I have the numerical value for L, I also have the numerical value for D, then I can work it out. So basically, that is how you can work out that. So that is how you can work out that. Okay, don't you think that here we have when substituting the limits we had made a mistake? No? Hello, excuse me, class. When substituting the limits here, what do you think? Did we substitute the limits correctly? Okay, so this x is just the argument of the function. The function here is the logarithm. So as I'm putting the upper limit, I'm taking the logarithm of the upper limit, then minus the logarithm of the lower limit. Are we together then? I'm taking the logarithm of the upper limit minus the logarithm of the lower limit. So what should happen is that this k and lambda are there, and then I'll say logarithm. Now let me put in the upper limit. Then the upper limit will give me L plus L squared plus d squared to the power half. That is for the upper limit. And then minus the lower limit. When I put the lower limit there, I have ln. And then we have seen that everything else will be equal to 0. Then what I just have is the d. So I have ln of that, then minus ln of d. And then if I work it out, then k lambda, and then ln according to the laws of logarithms, you know what this means. This means L plus L squared plus d squared, the power half, and then over d. I hope that we all know that what from the laws of logarithms that you learned in grade 11. So when you're subtracting the logarithms, then it is as good as dividing their arguments. Okay, so now you can proceed with those two steps that we had that we had done. K is equal to 1 over 4 pi epsilon naught. And then this will just be equal to the total charge over the total. Then you substitute them there. Then you have your final answer. Any questions? Any questions? Okay, no questions. So the other thing that we can talk about is the potential due to a charged isolated conductor. The potential due to a charged isolated conductor. Now, if we had learned in an earlier lesson that if you have a conductor, then all the charges will reside on the surface. The charges will reside on the surface of the conductor. And again, we said that the electric field will be perpendicular to the surface of the conductor. I think you remember those 2 points from the previous lesson. So what does it mean? If the electric field is perpendicular, if the electric field will be perpendicular to the surface, then what can you say about the electric potential? You remember the electric potential is basically the work that is done in moving a charge from one. So what is the potential from point A to point B? What is the electric potential? You see, at every point, the path is at right, it is perpendicular to the electric field. So remember the work. Remember what we had discussed about work. We said that work was equal to the force times the displacement times the cosine of the angle. So in this case, the force can be written as Q times E, the electric field. And then I have, are we together, class? Are we together?
Yes, sir.
So the force can be
Yes, sir.
written as Q times
Yes.
Yeah,
have the D. And then what is the angle between the electric field? What is the angle between the electric field and the displacement? Remember, you're moving from here up to here. So the
90.
angle is 90, so cos 90. So what is cos 90? Equal to 0. Okay, it's like this recording issue has become very, okay, thanks a lot for that reminder. But I think you, pardon me that I will not go back again to start explaining. I think this is already clear that, the surface of the conductor makes up an equipotential because there is no work that is required to move a charge on the surface of the conductor. So it is an equipotential because all the points on the surface are at an equal potential. So now the main point that I'm trying to explain here is if you have a sphere and this sphere is a conductor, if they ask you to sketch the potential inside the sphere and outside the sphere, what did we say? Inside the sphere, the potential will be constant. It will be just equal to K and then times the Q, assuming that Q is the total charge, and then over R, where R is the radius. So that will be the potential at all points inside, it will be a constant. What about outside? Remember what we had said? If you have a sphere, you can assume that it is the same as a point charge at the center. It will behave in the same way as a point charge at the center of that sphere. So it means that for all the points that are outside here, then the potential can be written as K and then times Q over this R. So now this R is not the radius, it is the distance from the center to the point outside the sphere where you want to find the electric potential. So it means that as this R is increasing, as you are going further and further away, what do you think will happen to the potential? It will reduce in this manner. It will reduce in this manner. If you try to sketch, this is a constant, this is also a constant. As you increase this, then this drops in that way. Okay? And then the electric field. How can you sketch the electric field? We say that if you have a conductor, then the electric field at all points inside that conductor must be equal to 0. Are we together? But then when you're outside this sphere, then the electric field behaves as if all the charge was concentrated at the center, then it will be K and then times Q over R squared. So you see this slope here, it will now be steeper. It will be more steep because it's now quadratic. It's now dropping off in a quadratic way. Okay, so it's very important for you to know how to sketch. You know, if someone asks you to say that, if you have a spherical conductor, can you sketch the electric potential and the electric field, both inside and outside? Then they are just basically looking for these two sketches that are here. Okay, so now we have learned how to calculate the electric potential from the electric field. So we say that if you have the, we have learned about this equation, minus the electric potential is basically equal to minus of this path integral. Minus of this path integral is the S. So it means that as long as you have the electric field, you can put the expression for the electric field in order for you to find the electric potential. Now, is it possible, what if what you have is the electric potential? Can you find the electric field? This is the subject now that we want to look at. If you have the electric potential, can you find the electric field? So let us suppose that you have a test charge Q naught and you move it through a displacement ds from an equipotential surface to an adjacent surface. So what is the work that you have done? We know that the work, I think we had learned the work that you have done is the minus of the change in the potential energy. And remember that work, remember the dV, it will just be equal to the work over Q. If you remember very well, we said that the potential is basically the work that is done per unit charge. So if you make work subject to the formula, it means that you are just cross multiplying there. Then the work, it will just be equal to the charge times the potential. So you have this. So it means that if you are moving a test charge Q naught within an electric field, the work that you have done will just be equal to minus Q naught, then dV. Okay? Now, you can also write the other expression, the work. Remember, work could also be written as the force times the displacement. Remember, the force and the displacement in this way, in this case, they are in the same direction. So it means that the theta is equal to 0, and then cos theta is equal to 1. So the work is basically the force times the displacement. But you know that the force here can be written in terms of the electric field as that. So you can just write it like that if you want. So this is the expression that is here. So you have come up with two expressions for the work. The work could be written as that, and also the work could be written as that. Now, since these two are the same, then you can equate these two expressions. So this, you write it, then it will be like that. And then this guy here, if you write it, it will be like that. Remember, it's a dot product. The dot product goes with a cosine. So this is that guy. This is that guy. You equate them. So in this case, you can make now this as the subject of the formula. Then you have that. Okay? And now this expression is what we want to look at. You can see that in this expression, if you have the potential, if you differentiate the potential with respect to this direction, this is basically the direction where you are actually moving, then you'll be able to find the electric field. So in short, we are saying that the component of the electric field in any direction is negative of the rate at which the electric potential changes with distance. I repeat.
Transportation for us for today, but it's not possible.
I repeat, the component of the electric field in any direction is the negative of the rate at which the electric potential changes with distance in that particular direction. So in short, we are saying that the ES, remember ES is basically the component of the electric field in a certain direction, is just basically the rate at which the potential changes in that particular direction. Okay, so you know that if you take the three-dimensional coordinate system, then the directions will be X, Y, and Z. So it means that the X component of the electric field will just be equal to the rate at which the electric potential is changing in the X direction. The Y component of the electric field is the rate at which the potential is changing in the Y direction. and the Z component of the electric field is the rate at which the electric field is changing in the Z direction. So it means that if you know the electric field, then you can actually be able to find the components. And after you find the components, you can actually find the magnitude of the electric field by using this equation. You know that EX squared plus EY squared plus EZ squared. Okay, so in short, we are saying that if you know the electric field, you can find the electric potential by using this equation. But then if you know the electric potential, you can find the electric field by using any of these three equations or a combination of them. You stop me if you have a question. Okay, so now electric potential energy. We have already seen that when you do work on a system, then that work becomes stored as potential energy. That is what this equation is telling us. When you do work, for instance, in this situation, if you have two charges here, it means that this charge here is producing an electric field, and that electric field is exerting a force. And if this charge that is here, it moves by a certain distance like that, it means that okay, so I'll repeat what I was saying. I had a break in the network. So what we are trying to say is that if consider two charges that are in a certain regional space, it means that, for instance, this charge 1 has got an electric field associated with it that is going radially outwards like that. And if you bring charge 2 within the vicinity of charge 1, it means that there will be a force. There will be a Coulomb force that will be exerted on charge 2 due to charge 1. And then if that force manages to move this charge 2 in that way, it means that work has been done. Now, if work has been done, it means that that work is stored as the potential energy. So this work that has been done by the electric field, it is stored as the potential energy. Now, remember, the work is basically the force times the displacement. The force can be written as Q times E. So it means that this equation here can be written like that. All right? In a previous lecture, we had learned about the applied force. In order for this charge here to move quasi-statically, it means that there must be an applied force in the opposite direction. So the work that is done by the applied force is just equal to the minus of the work that is done by the electric field. If you combine these two equations together, you combine these two equations, this one and that one, then you find that the work that is done by the external agent, the applied force, is just stored as the potential energy. Okay, so now what we want to do is that if you have, remember, electric potential is basically the work that is done in moving a charge from a certain point up to infinity, if you remember what we had said. So if you had a charge, the work that is done in moving, if this charge is done moving from a certain point to another point, then we don't call it absolute potential. We only call it absolute potential if this charge goes all the way up to infinity. Infinity is the point where the electric field is effectively equal to 0. Okay, so now the potential, the electric potential can be written as 1 over 4 pi epsilon naught, which is just equal to K, and then Q1 over R. This is the electric potential due to this charge Q. Now, what is the potential energy? See, remember we had a charge Q2. So what was the potential energy that is stored when you move this charge Q2 up to infinity like that? Then that potential energy will just be equal to Q2 times the V. Remember, V is given by this formula. So it means that the potential energy, you are just multiplying this times that. Then you have this. This is the potential energy, which is the stored energy. So you remember, this is only applicable if you have two two charges. What if you have more than two charges? If you have, you bring in another charge like this, you bring in another charge like that, then you realize that as you are bringing another charge from infinity, now you have to do work against Q1 and also against Q2, because as you are bringing this charge from infinity, there is a force that is coming from Q1, you see, in that direction. There's also another force that is coming from Q2 in that direction. So you are actually doing work. Now, this work that you are doing is also stored in as potential energy. So in short, you are saying that now, since you have three charges, then the total potential energy will be the potential energy due to 1 and 2. You see, the potential energy when between 1 and 2. And now you have, as you are bringing in charge 3, you have the potential energy. You are doing work against charge 1. So you can call the potential energy as the potential energy on charge 3 due to charge 1. So you have this potential energy here. But again, you also have the potential energy due to charge. You have the potential energy due to charge 2 of charge 3 that you can denote as this. So the total potential is just U12 plus U13 plus U23. Now, it means that, you know, this is a common factor. You can factor it out. And then when we say U12, it means that you are just talking about these Q1 and Q2. So you have Q1, Q2 over R1, 2. And then this guy here, it means that you are saying Q1, Q3 over R1, 3. This guy here means that you are saying Q2, Q3 over R2, 3. So the total potential energy that is stored in that system of charge is just given by this formula. Any questions before we proceed? Any questions, ladies and gentlemen? Are we there?
No, sir.
No questions, okay.
Yes, sir.
All right, so then we have come to the end of this lecture slide. And this is the summary of everything that we have done. So we have talked about the electric potential energy. So we say that if you move a point charge from an initial point I to a final point F within an electric field, then you have actually done work, and that work is stored as potential energy. We say, so this mathematically can be represented, the potential energy is just equal to minus W. Why is the minus there? It is there to signify the fact that that energy is stored in the system. And now this work here represents the work that is done by the electric field, right? The other point that we had discussed was to do with the electric potential difference between 2 points. So the electric potential difference between 2 points is basically given as the change in the potential energy between those 2 points per unit charge. The change in the potential energy between those 2 points per unit charge. Remember, the change in the potential energy is connected to the work done. So in short, you can say that the change in the electric potential is basically the work done per unit charge. That is also an equivalent way of saying the same. In this same lecture slide, we had talked about the equipotential surfaces. We said that these are surfaces where all the points on that surface have the same electric potential. So on an equipotential surface, no work is required to move a charge from one point to the other on the equipotential surface. And then we mentioned that the electric field is always perpendicular to the electric potential, to the equipotential surface. The electric field is always perpendicular to the equipotential surface. At that particular point, I think we are going to come to a conductor anyway. So if you have the electric field, then you can find the electric potential by using this equation. You are doing an integral from the initial point to the final point of the path integral of the electric field. So if you do this integral, then you would have found the change in the potential. Now, just to remind you that this change in the potential, if you want to find the absolute potential, then you must talk about the work that is done by moving the charge from a certain position to infinity. We had discussed what infinity is in terms of the electric field. We said that this is the place where the electric field is effectively zero. And then we also talked about the electric potential due to a collection of point charges. So we just used the superposition principle in order to find the electric potential at a certain point due to a system of point charges. So you are just doing an algebraic sum. Remember what we said, an algebraic sum or an arithmetic sum, where if the charge is a negative, then the potential will be a negative given by that formula that we had discussed for the point charges. And then we had also discussed the potential due to a continuous distribution of charge. Due to a continuous distribution of charge, I think there we actually said that you must assume that that charge is made up of an infinite number of small charges, each of which could be considered to be a point charge. So from there, you could start from the contribution of one of those small charges to the electric potential at a certain point. So you consider it as a point charge, and then you write that the charge in terms of the charge density, and then you do appropriate integrations in order to find the total electric potential due to the entire charge distribution. And the other point was we reminded ourselves, we learned about the electric potential associated with a charged conductor. We say that if you have a conductor that is charged, then the surface of that conductor makes up an equipotential surface. It means that the potential at all points on that surface is the same, and therefore no work is required to move charges over that surface. I think towards the end of the lecture slide, we discussed how to calculate the electric field if we have the electric potential. Okay, we saw that in each of the directions, the component of the electric field in each of the directions was just given by the rate of change of the electric potential in that particular direction. So you could use the X direction, the Y direction, or the Z direction. A combination of these could give you a general equation like this. And finally, we said that as you are, if you are arranging a configuration of charges, in order for you to arrange a configuration of charges, taking them from infinity up to a particular point, you are actually doing work. And the work that you are doing will be stored as potential energy within that configuration. So you can speak of the electric potential energy of a configuration of charges, and then we saw how to deal with that if those charges were actually point charges. And that is how we ended this class. Unless there are any questions. Any questions? Any questions? Okay, so since there are no questions, I would want to end this class at this juncture, since you people don't have any questions. But before I end it, maybe let me just give the chance to Mr. Who, the one who had asked that question earlier on the. Okay, we had the student who had asked a question earlier on. I think it should be on when you are moving a positive charge in the direction of the electric field, something like that. do you still, Mr. Mchimba, do you still remember that question? Mr. Mchimba?
Yes, I meant that point you said the direction of the electric field.
Yes.
The electric field is in the direction of the decreasing electric potential.
So that question has not been addressed yet, right? You would want us to talk about it before we leave?
Maybe just a bit, sir.
Okay, let us go somewhere there and see. Okay, so the place where we had talked about that is somewhere here. I think if I remember well, I think the point that you are trying to say is this: a system consisting of a positive charge and an electric field loses electric potential energy when the charge moves in the direction of the field. Is this the one that that?
Yeah, actually, that's the one.
That is the point. Okay. So
yes.
Let us try to explain it in this way. So we are saying that a system consisting of a positive charge. So if the charge is positive, and then it is moving when the charge moves in the direction of the electric field. When the charge moves in the direction of the electric field, so it is more like it is on a slope, on a downhill slope. Then we say that it loses the potential energy. Now, how can we understand this? Let me try to zoom on one of these diagrams here. Just on this diagram, are you able to see my screen?
Yes,
so
sir.
if you have this charge here,
yes, sir.
It is in an electric field. In what direction is the electric field? In this, for the purposes of this diagram, the electric field is downwards. Correct?
Downwards, yes.
Yes. Now
yes,
imagine what would happen to this charge if you were just to let go of it. You let go of it. What would happen to the charge? Will it move upwards or it will move? Will it move against the electric field or it will move in the direction of the electric field?
I think in the direction of the electric field.
Very good. It will move in the direction of the electric field. Now, as it is moving in the direction of the electric field, it is just moving spontaneously.
Yes.
Are we together? It is just moving spontaneously.
Yes.
So, would you think that it is losing? If you know, think about it in terms of gravity. If I lift something up and I let go of it, it moves on its own. It moves spontaneously on its own. Not so? So is it losing? Is it losing potential energy or it is gaining potential energy?
Actually, it's losing.
It's losing. So this is exactly what is happening. So when I just leave this charge just there, it will on its own it will start moving in that direction. It means that it is actually losing potential energy. Now, what if I was going to hold this and then I drag it in the other direction, in the opposite to that of the electric field? Okay, that is similar to taking something from the ground and I'm lifting it against the gravitational field. Have you seen? So in that particular case,
yes, sir.
Is it gaining or losing the potential energy?
It's gaining.
It's gaining. So this is the analogy that we are trying to draw here between there.
I get the point.
Okay, okay. So thank you very much, ladies and gentlemen, and I would want to end the class at this point. Thank you very much for being around. I'll see you next time when we meet. Have a good day.
Would you maybe, sir?
Yes, please. Yes.
Would you maybe just would you just emphasize maybe on the most important formulas we are supposed to, sometimes it's very important to know the most important formulas in this.
All these things that we are learning are the most important. I will not lie to you to say that this is important, this is less important. All these things that we are learning are very, very important. They are the most important. Okay, so so in short, I think, by the way, in order to demonstrate, how these equations are coming, because I know sometimes there's a temptation to think that if you just master one equation or two equations, then you'll be able to solve everything. That could not be possible. Okay, so we have to apply all these things that we are learning to solve different types of problems. So when I think before the end of the day, maybe the class representative should remind me so that I give you the tutorial sheet back, just for the sake of practicing on how to solve the problem. Okay?
Thank you, sir.
Okay, thank you so very much. Thank you.